Let's take the derivative of the inverse secant function. So we have y equals arcsecant of x. First thing we're going to want to do is take the secant of both sides. So secant of y equals secant of arcsecant of x. And secant of arcsecant of x is just going to be equal to x because secant and arcsecant are inverse functions and they're going to cancel each other out. So we have secant of y equals x. Now we're going to want to take the derivative of both sides. So we have the derivative with respect to x of secant of y. Notice here that we have a function of y and we're differentiating with respect to x. So we're going to have to use chain rule there. Equals derivative with respect to x of x. And that's just going to be equal to 1. Derivative of x with respect to x is just going to be equal to 1. So now on this side we have dy dx using chain rule times dy of secant of y. We're just going to go ahead and complete that derivative. So we have dy dx times the derivative of secant y with respect to y is going to be secant y times tangent of y. That's going to be equal to 1. So let's go up to the top for a second. Notice that we have y equals arcsecant of x. So if we take the derivative of y with respect to x, that's the same thing as saying the derivative of arcsecant x with respect to x. So we're actually going to go back down here and notice that we have dy dx. So we're going to want to solve for this. So in order to do that, we're going to divide both sides by secant y times tangent y. So secant 1 over secant y times tangent y. And we have the derivative of y with respect to x now, but it's in terms of a function of y. Now, that's fine, but generally we're going to have access to inputs of x and not y. We're going to have access to inputs of the independent variable. So we're going to want to rewrite that in terms of x. In order to do that, we can use a trigonometric identity from earlier in the problem right here. Secant of y equals x. Let's write that out. We have secant of y equals x. Now remember that secant is another way of saying the hypotenuse over the adjacent side. So if we draw out a triangle here, a right triangle, with an angle y here, we can say a hypotenuse of x and an adjacent side of 1 will result in secant of y equaling x. So we can say x and the hypotenuse and adjacent side equal 1. But hold on a minute, because when we're dealing with a reference triangle, although people often omit this, we're dealing with a set of vectors. So this, in the I direction, the adjacent side is going to have both direction and distance. This, in the j direction, is going to have both direction and distance, up and down, and adjacent was left and right. The hypotenuse is just the distance between the endpoints. So the endpoints are going to be the origin and the addition of the two vectors. But that's just a raw distance. That is a scalar distance. There is no direction given. And by definition, a distance is a positive entity. You can have a distance moving in the negative x direction, You can be moving in that direction, but the distance you're moving in that direction is still a positive. You can move in the negative y direction, but if you move in that direction, it's a positive distance in the negative y direction. So since this is a raw scalar, then it's also, by definition, always going to be positive because it's just the distance. So that actually, as is, isn't going to work for us. We would like to find some way to rewrite this same triangle, but rewrite it with functions that aren't potentially going to be negative. So x could be -1, it could be -2, it could be +1, it could be +2, and so on. If it's negative, any functions that we create out of this triangle are going to be incomplete for negative values. So we can actually rewrite that triangle using a second trigonometric identity, and that's going to be, since we know secant equals hypotenuse over adjacent, and we also know cosine in general equals adjacent over hypotenuse, what we can say is that we have a hypotenuse equal to x. We have an adjacent side equal to 1. So cosine of y is going to be equal to 1 over x. But wait, there's one more thing that we can say here, is that cosine of x, since it's equal to adjacent over hypotenuse, what if we just say the adjacent side is equal to 1 over x and the hypotenuse is equal to 1? That satisfies the same needs. Let's rewrite the triangle now, where we have our right triangle with angle y, where the adjacent side is equal to 1 over x, and the hypotenuse is equal to 1. Now we can just, now that we don't have any functions in the hypotenuse that could potentially be negative, we can use the Pythagorean theorem, find this last side, and finish our problem. So we have opposite squared plus adjacent squared for the Pythagorean theorem equals hypotenuse squared. Now we know that the adjacent side, we're solving for the opposite side, so we say opposite squared plus 1 over x. That whole thing is squared. That's just going to be equal to 1 over x squared equals the hypotenuse, so 1 squared, which of course is just going to equal 1. So we have opposite squared, subtract 1 over x squared from both sides, and we get 1 minus 1 over x squared. To finish solving for the opposite side, we're just going to take the square root of both sides. Get rid of that. Equals the square root of 1 minus 1 over x squared. So it might occur to you at this point that, you know, for all these other problems, why do we keep taking the principal root? Why isn't it that we have a case where we do plus or minus? Why don't we do that? The reason is because those sides, the opposite and the adjacent sides, are representing distances. Just like up here, the direction is given by the x. So if this side here is going to be moving in the negative x direction, that would be represented by 1 over, say, -1 or 1 over -2. So it's the idea that we're not moving a negative distance. We can be moving a positive distance in the negative direction. So let's go ahead and insert that principal root, 1 minus 1 over x squared. And so now keeping in mind that we're solving for secant y times tangent y. So secant, like we said earlier, is equal to the hypotenuse over the adjacent side. So secant of y is going to be equal to the hypotenuse is 1 over the adjacent side, which is 1 over x, which is just going to be equal to x. So we're going to multiply the root by the reciprocal of the denominator. Now the other thing that we're looking for is tangent y, and tangent is equal to opposite over adjacent. So tangent of y is going to be equal to opposite side, which is square root of 1 minus 1 over x squared, over the adjacent side, which is 1 over x. And that's going to be equal to x times the square root of 1 minus 1 over x squared. Now that we have both secant, which is equal to x, and tangent of y, which is equal to x times the square root of 1 minus 1 over x squared, we can rewrite dy dx. So dy dx is going to be equal to 1 over x, secant of y equals x, times x square root of 1 minus 1 over x squared for tangent. We have just one more multiplication to make. So we have dy dx equals 1 over x squared times square root of 1 minus 1 over x squared. And since this is the last line, let's make that a little neater. 1 over x squared. And we are done.